Yeah, thanks, Helen, and thanks, Nathan, for that introduction. And it's interesting talking about the prospectivity up in that neck of the woods, because I think it's really due for a new round of discoveries. And one of the things that certainly struck me as we were putting the Northeast Queensland Deposit Atlas together was that a lot of these deposits, I guess, as we know, were discovered quite a while ago, early in the 1900s, for example. And like so many deposits, as processing technology progresses, and Nathan was talking about ore sorting, for example, using optical and other methods, these deposits come to be reevaluated. So that there are a lot of these, I guess, older deposits there. But I guess my feeling from putting a lot of this work together is that together with the pickup in new economy minerals and all the renewed interest in tin, for example, is that it's probably about due for another round of exploration with new technologies and maybe not so much new conceptual thinking about the deposits, because the styles are pretty well understood. But I think with new technologies, it'll be seeking those tin and tungsten deposits that are hidden under 50 metres and potentially flat lying, for example, rather than steep vein deposits. Anyway, that's my thoughts anyway. I would like to acknowledge again the GSQ and a round of people from both GSQ, Coralie Siegel from CSIRO, and a host of people from SMI who've been working on these atlases. And as always happened, I noticed looking at Nathan's slide that I left off the geophysicist Sasha, so I'll give her my acknowledgements. Thanks, Sasha. Now, here are a couple of links to the Mineral Deposit Atlas. You'll find them on the GSQ data portal, and then also the tin tungsten compilation link on the data portal as well. So newly minted and up on site. So thanks for that. Look, I won't talk too long about the Deposit Atlas because time is short, but I think quite a few people will be familiar with the Northwest Queensland Mineral Deposit Atlas, and obviously the Northeast Queensland follows a similar sort of theme. And the theme for those is that we're essentially looking at ways that we can present and compile information from deposits, particularly to do with what the deposit itself looks like, but also its halo and its signature in various data sets, so that explorers, when they want to be getting on the ground there, can actually understand potentially what the signatures and halos of these deposits look like, so that when they're on the ground drilling a hole or on an outcrop, they can sort of put that geology that they're looking at potentially into context from what some of these deposits look like. So that's sort of the rationale. And in the Northeast Queensland Atlas, there are 11 deposits, or some of them are actually fields, for example, out around Tate River, the alluvial tin field, for example, and they cover 4 metal associations. So Nathan briefly touched on those 3 tungsten deposits that are clustered, here we are, Watershed, Mount Carbine and Wolfram Camp. There's the one nickel scandium deposit down at Scone, which incorporates these 3 laterite deposits, Kokomo, Greenvale and Lucknow. And then there are 6 tin deposits or districts that we talk a little about. And then there's one base metal and tin, base metals and tin component at Mount Garnet. There's both base metals, skarn mineralisation, as well as tin mineralisation. So the chapters in the Atlas cover those 11 deposits or fields, and it's really interesting reading. It's a great polymetallic terrain up there. So in terms of delivery of the atlases, there's the hard copy, which is a PDF document. Well, so it's not hard copy, but it's digital. And you'll find those at the website. There's 3 examples of the cover pages for those 3 tungsten deposits. And as well as the hard copy, we also have the 3D data compilation and model, or sort of a 3D GIS. And what we've done is take as much data as we can. Some of it kindly provided by deposit owners, others taken out of the public domain information. Put it all into 3D so that you can really get a feel for what the geometry of that deposit looks like, and where those halos and mineralogy and geophysical signatures, for example, sit around that deposit. So it's the hard copy, it's the digital data. We also provide all the base data so that if people are not using Geoscience Analyst, which is the platform we've used, they can pull that into whatever their favourite software is. Now, these are the links here. This is the GSQ data portal, and then the SMI website down the bottom. So plenty of places to access all this information and data. There's something's popped up. This is the type of 3D data. For example, this is from Wolfram Camp, I think, showing the molybdenum isosurface in that horizon on the granite contact. So that's the sort of data that we've included where we could get our hands on. So that's the Northeast Queensland Mineral Deposit Atlas, and it sort of goes hand in hand with the tin tungsten compilation that we've been doing, albeit the tin tungsten compilation, the brief is more Queensland-wide, not specifically Northeast Queensland. So you would have seen this plot before. This is the type of table that we've been using for the intrusion-related tin tungsten deposits. I guess in contrast to the cobalt deposits that we were talking about earlier, tin tungsten is an order of magnitude in terms of deposit models more ordered and understood from what I've read, and that goes from the type of cross section that Nathan was showing, where you have your vertical section through the body, and you go from having your grisons down around the granite up into having your veins, etc. For example, in Northeast Queensland in the Hodgkinson formation, and that's reasonably well understood, as is the association of tin tungsten deposits with dominantly reduced and highly fractionated felsic intrusions. And if you look back at the work that's been done, all that great work that was done by Roger Taylor back in the 70s, mapping the metal zonations out from the granites, essentially down temperature, I think. So they're reasonably well understood. So we've basically run with one intrusion-related tin tungsten model. Now, I must admit my background is not in igneous petrogenesis, so it was positively fascinating to get into the tin granite story. And really, once you have a good look at it, what you understand is fractionation and reduced granites are key. And so I thought I'd just put in a quick primer here on a couple of the plots for typically how people classify their granites. And so you'll see this plot on the left on the x-axis is rubidium over strontium, and then on the y-axis is Fe2O3 on FeO. So basically plotting your fractionation and your oxidation. And this plot is from Blevin et al., 1996. And it really nicely shows in these magmatic systems how your your metal associations vary with your fractionation and oxidation. So that essentially when we start looking at more the tin tungsten, the tungsten sits a little bit to the left on here, but we're essentially going to be looking at this part of the field. And so when we step down in this presentation, we'll have a look at the distribution of fractionated granites. We'll basically be using probably around about the ratio of 10 of rubidium strontium. So we're looking to the right on this diagram. And then this is from Champion and Heinemann, 1994, looking at plotting your granites as strongly reduced, oxidized, or strongly oxidized based on your iron speciation. So that's just a bit of a primer for how we're going to be looking at these metal assemblages here. So one of the key things we did was put together the fractionated granite data sets, and I guess anybody. I grew up studying in Victoria in my early years, and you learn that Eastern Australian granites were a pretty well studied topic, and you see that in the data sets that we pulled together. There's incredible amount of data through Eastern Australia from igneous rocks, whole rock data, So what we've done is go to a lot of those studies of granites of Eastern Australia, and you'll see the names of the studies down here, and they essentially put together whole rock databases from the literature and the survey, et cetera. And some of them have classified granites based on their fractionation. Some of them haven't. For example, with Siegel, I actually took her rubidium strontium values and we converted them into, if it's greater than or equal to 10 being fractionated. Some of the other studies had already classified them into fractionated, etc. So we took those studies, all of which had different geographical areas of coverage, and we put them all together to basically look at where is the occurrence of fractionated felsic rocks in Queensland. And you'll see that it is very strongly dominated by northeast Queensland. There are also some fractionated rocks, felsic rocks out around Mount Isa, as well as down in the southeast here. Something else we've looked at is these great catchment geochemistry data sets. And we've used two data sets. We've used the NGSA, the National Geochemical Survey of Australia, from Geoscience Australia. And we've also used the Cape York catchment assessment data from the GSQ, which is a more detailed survey, but pretty much using the same methodology as the NGSA. So we put that data together to try and tackle these metal associations, and the obvious elements that people or that we see with these tin granites are fluorine, boron. We just heard Nathan talking about the tourmaline at Mount Carbine, and we've also put together a what we call a tin index of lithophile elements. So that there are 8 elements, I think. And I've normalised them on a rank percentile and simply summed them to try and map out the tin index so that there are places that we can see that are not specifically associated with the known tin domains. And you'll see the way that looks is northeast Queensland is certainly there. We find some of these areas further down to the south as well, down around the Texas sub-province in particular to the south here. So that's one of the data sets we've taken. It's absolutely fascinating data sets and well worth a look. We've also used the regional geophysics and we've used that to look at granite geometry. Okay, so on the left here. This is an area from down south of Herberton, I think, somewhere. But if you look at the magnetic data, what you can see, this Pluton C down here is obviously steep-sided, and the erosional surface would be cutting through that granite. You look at intrusion A, which there are a few small outcrops here through the cover, and you can see that is essentially a small outcrop of granite. But when you look at the magnetic data, you can see this thermal aureole, presumably magnetite creation through thermal metamorphism. So that out here, you can actually see that you are sitting in the shallowly dipping shoulders. Sorry, that should have a U as well there. A shallowly dipping shoulders of this granite. And these are the sorts of things that you want to be thinking about if you're thinking of the model of ascending fluids from a granite. And we saw Mount Carbine and those other tungsten deposits that sit up or adjacent or up, we're not sure yet, in the Hodgkinson Formation away from the granite. So it's the regional geophysics, the magnetics in particular, is really, really good for showing you where you are in the geometry around those plutons. We've also used the mag to have a good look at the degree of fractionation. And you can see here that in red are the fractionated felsic units from the various studies, and they are in this area. They're pretty much all non-magnetic. So the regional geophysical data is giving you a really good lead in to which of these plutons in this area might be your fractionated units, and you'll see that these highly magnetic granites here, none of those fall into those fractionated categories. So the magnetic data is incredibly useful. It's interesting. We didn't go in detail into the radiometric data, but at first glance, the radiometrics was a much more complex story in terms of trying to map out fractionation and oxidized versus reduced. So, but to spend a bit more time on it, I'm sure there will be some conclusions drawn from the radiometrics as well. On the other things we used regional geophysics for was as part of, I guess, the mineral systems model. If you look at the amount of felsic magma you need to have, and you look at its average tin contents, and you look at then you do basically the mass balance with your tin to what you need to produce those deposits. You really need large batholiths of felsic material. So what we did was go through the gravity data, and in these areas we didn't do it over the entire state, but in the areas that we knew there were these fractionated granite domains, we went through and mapped out from the gravity. You can see there where those low density large plutons, presumably with quite a bit of depth extent because they have the low gravity response, and use that as one of the tools to say, well, you want to be near a large mass of felsic magma. So that was the gravity data. And the other thing we used the airborne magnetic data for, in conjunction with the gravity, was to look at the geometry of some of these Paleozoic felsic plutons and say, can we look at the way they were emplaced and understand from their geometries what potentially was happening with syn emplacement structural movement. And you look at some of these granites and the way you look at their geometries, and you start to think, are these structurally controlled emplacement of granites, and that's obviously syn emplacement time. Can we be using these structures and orientations to be thinking about where we should be moving from the granites to echo where those fluids might be going. So yeah, the geophysics seems pretty important up in this neck of the woods. So just to summarise, because I'm aware time's ticking on, is this is the target areas. Basically, a lot of them up in northeast Queensland. You can read all about them in the report. Some of them out around Mount Isa. This is mainly reduced, tied into fractionated rocks around Mount Isa, and also up around the Murphy Ridge, way up here on Cape York, and then some of these, the Texas province with the tin fields is another obvious candidate. But then the Mundubba area also comes up as looking positive on the basis of the fractionated granites there, and also some various tin and tungsten occurrences too. So there's sort of the main cluster of target areas. In a bit more detail out around Herberton. We didn't focus so strongly on Herberton simply because there's been so much work there, and we're really looking for these other areas that might be prospective, where people perhaps haven't spent so much time working. So, for example, where we see these fractionated felsic rocks, and they're on these lobes in the large batholiths, maybe this is the sort of place where you're seeing the evidence of the fractionated rocks, and you've got the volumes of magma to potentially give you the fluid that you need. So they're the target areas. You can go and see them in the report. Here's the link to the compilation that's gone up. I guess in summary, the majority of the prospectivity in Queensland appears to be in the Paleozoic and the early Mesozoic, I guess, on the eastern seaboard. Albeit having said that there are some potential areas. We didn't mention Croydon as well, further out west. The tin tungsten models are strongly dependent on granite petrogenesis, of which there is a long history of work in Eastern Australia, and we've pulled together those databases regarding granite fractionation and oxidation state, so that is hopefully there for people to work with. And I guess my forward-going comment is that we've had a look at the geophysical data, particularly the aeromagnetic data, but I know if I was going into those terrains, I would be having a long, hard look at how we incorporate this granite in detail, the granite data with the geophysical data, because I was talking earlier about these older deposits these deposits that were found more early on at surface, and the next wave might be a little bit lower, 50 or 100 meters under cover that don't have a lot of halo at surface. But having a good look at the geophysical data might be able to tell us about the granite geometries and the structure in the area, so you can start honing in on these data. So I think it's an incredibly interesting place, and all that data's up there on the web. So please go and have a good look at it. So thanks for that. I'll stop sharing there.
Wow, thanks, Paul. And look, it's bringing it all together with the different series from the compilation. What are the other ones that are still to come? Today we've heard rare earths, cobalt, silica, tin tungsten.
Yes. Yeah. What we're still working on is indium, molybdenum, gallium, germanium, and scandium. So there are those ones still to come. As you can see, we dig and just want to dig deeper. It's all this data. Yeah.
No, there's always more. The more you look, there's more to do, isn't there? So I guess for the audience that's hung in, just stay tuned, because there is a lot more to come in terms of all the data that Paul, Nathan, Rick, Katerina, and many more are pulling together. And I think, as you can see, it's a really, really valuable set of compilations, targeting tools, and just, circles on the ground. Let's see how much we should do a test and see how much of that ground is currently under tenure, and whether it stays that way.